We've got one more set of factoring techniques to talk about, and we're going to be talking about how you can factor things that have two terms. So we factored trinomials in the previous lesson, and the lesson before that we factored things with four terms. And so something with two terms can only be factored if it fits into a special pattern. And the first pattern we're going to learn is the difference of perfect squares. I have the formula included in the notes. It basically says anytime you have a difference, so subtraction, with two perfect squares, it can always be factored. And I'll just show you how this works with an example. X squared minus 49 is the same thing as x squared minus 7 squared. So using this pattern, the a is the x and the b is the 7. I get x plus 7, x minus 7. In my second example, 4 is a perfect square, it's 2 squared. 25 is a perfect square, 5 squared. So using my pattern, the a is 2y, the b would be 5. I get 2y plus 5, 2y minus 5. Just like in the previous sections, we should always look for a greatest common factor first. And this problem does have a greatest common factor. We can take a 2 and a y out of both terms. If we pull the 2y out, we are left with y squared minus 4, and there's our difference of perfect squares. The y squared minus 4 can be factored as y plus 2, y minus 2, and make sure you include that GCF in your final answer. Okay, one more example that's a difference of perfect squares. At first glance, this problem looks a little bit different because it has an x to the fourth in it. However, x to the fourth is the same as x squared squared, and 16 is a perfect square, it's 4 squared. So using my pattern, the a is x squared and the b is 4. I get x squared plus 4, x squared minus 4. Now we can actually go a little bit further with this. I see another difference of perfect squares. The x squared minus 4 can be factored as x plus 2, x minus 2, but notice that sum of perfect squares that actually cannot be factored. We just leave it as x squared plus 4. Now we've got two more patterns that can be factored, and that would be a difference of cubes and a sum of cubes. And I have the formulas included in the notes. These are formulas that you don't need to memorize. They'll be provided to you exactly like this on exams. In these problems, we're going to be looking for perfect cubes. And so I just put up a list of some common perfect cubes. So 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. Those are some numbers that I'm going to be looking for. This first example, x cubed plus 8, I notice that 8 is 2 cubed. This is a sum of perfect cubes. I'm going to use that second formula listed, replacing all of the a's with x's and all of the b's with 2's. Once I plug the numbers in, there's not much I can do other than maybe changing the 2 squared into a 4. And this is my final answer, x plus 2, x squared minus 2x plus 4. We cannot go any further with this. That trinomial actually cannot be factored. There are no numbers with a product of 4 and a sum of negative 2. Now, just like in the previous examples, sometimes you might see a GCF, and in fact, you should always look for a GCF first when you're factoring. In this problem, the GCF is 2, and if I pull the 2 out, I'm left with a y cubed minus 27. This is now a difference of perfect cubes. 27 is 3 cubed. So I'm going to use that first formula that was on that previous page. I'm going to replace the a's with y's and the b's with 3's. I make sure that I include that GCF. The 2 is going to stay in front of the problem. And so my final answer is 2y minus 3, y squared plus 3y plus 9. Just like before, we can't go any further with that trinomial. That's always going to happen in these problems. Once you use your formula, you're going to be done with the problem. Now part C is also a difference of cubes. 8 is 2 cubed, and 27 is 3 cubed. So when I use my formula, I'll be replacing the a's with 2p and the b's with 3. After I plug those numbers in, I've got a little bit of work to do. I'm going to square both the 2p and the 3. The quantity 2p squared is 4p squared, plus 6p, plus 9. And that's my final answer. Finally, let's put all this together. On exams, the factoring problems are going to be all mixed together, and so you're going to have to pick which strategy to use. And so I have written out in the notes my advice. In each of the problems you're given, the very first thing you're going to do is look for that GCF. And then the method you pick depends on the number of terms. 4 terms, we do the grouping. 3 terms, we either use trial and error or the AC method. And if we have 2 terms, we'll use one of the formulas we learned today. So let's run through a couple of mixed examples and see how to apply these strategies. So example 1a, first thing I do is look for a GCF. It is 3x. If I pull the 3x out, I'm left with x cubed plus 8. I have 2 terms, so I check to see does it fit into any of my formulas. And it does. 8 is the same as 2 cubed, so this is my sum of cubes formula. When I use the formula, I'll be plugging in x for a and 2 for b, because 8 is 2 cubed. I keep the GCF in my answer. The 3x is part of the answer. And then I plug in the x's and the 2's. And my final answer is 3x, x plus 2, x squared minus 2x plus 4. Example B, I start by looking for a GCF. I think the GCF here is 3x. 30 and 18 are divisible by 3. And you could double check in a calculator. 57 is also divisible by 3. If I pull out the 3x, I'm left with 10x squared minus 19x plus 6. I have 3 terms here. There's a number in front of the x squared, so I'm going to use the AC method. 10 times 6 is 60, so I need 2 numbers with a product of 60 and a sum of negative 19. So I start by making a list. Once I get to 4 and 15, I think that will work if I make both of them negative. So I'm going to keep the GCF in front. I don't want to forget about that. I copy down the first term. I break the middle term up into 2 terms using those numbers I found. Copy down the last term. I can pull a 2x out of the first 2 terms. And I'm going to pull a negative 3 out of the second 2 terms. Taking out that negative changes the signs. I bring the 5x minus 2 out front. I'm left with a 2x minus 3. And finally, make sure you include that GCF, the 3x, in front of your answer. Example C, we start the exact same way. Look for a GCF first. There are x's in both terms, so I'm going to pull an x out. If I take an x out, I'm left with x minus 9. And there's actually nothing else we can do with this. Some people might be tempted to call this a difference of perfect squares, but because you don't have an x squared, that's it. You're done with the problem. And finally, one more example. I'm going to start by looking for a GCF. There is none here. I have 3 terms, so I can use trial and error or the AC method. There's no number in front of that x to the 4th, so I'm just going to use trial and error. Because I have an x to the 4th, when I factor, my binomials are going to have to start with an x squared. Then I have to find 2 numbers with a product of negative 20 and a sum of 1. 4 times 5 is 20, and if I make the 5 positive and the 4 negative, it adds up to the 1. Now I'm actually not done here. If you look carefully, there's a little bit more factoring that we can do. I see an x squared minus 4, which is a difference of perfect squares. I can factor the x squared minus 4 as x plus 2, x minus 2, and then notice that there's nothing I can do with the x squared plus 5. That just stays there. Okay, so to summarize, make sure you look for those GCFs before you do anything else, and then pick your factoring method based on the number of terms in your problem. Hope this helps, and as always, please let me know if you have any questions.